I'm hoping that physical and chemical properties is also something that you are familiar with. Physical properties are those that can be observed without changing the original composition of a substance. And by the original composition, we're meaning like the molecular structure. So for example, let's think about water. Water's formula is H2O. Water is H2O. What properties can I observe about water without changing that structure of the water molecule? It's 2 hydrogen and 1 oxygen bonded together to form this molecule. Examples might be things like phase or state of matter. Now I can observe if water is a solid or a liquid or a gas, and I don't have to change the original structure of the particles. I'm just making an observation, a physical observation. Hey, it's an ice cube, it's solid. Ooh, I see water in the liquid phase. Things like color, texture, odor, and the list goes on and on. Things like solubility, magnetism, etc. And I can think of tons of them. Things that I can observe about a substance without changing the structure of the molecule or the particle. I can look at a sample of, I don't know, copper, and I can observe its color. I can observe its texture. I can smell a sample of sulfur. I can put salt in water, and I can observe its solubility. Does it dissolve in water? Now here's kind of a tricky one, because sometimes people don't really know where to put solubility. Well, think about, okay, if I dissolve salt in water, can I get the original salt back without changing its structure? I'm hoping in your mind you are saying yes. What if you just evaporate the water? If you take salt water, you put it on a hot plate, put it under a Bunsen or over a Bunsen burner. Sure, the water will boil off, the water will evaporate, and you should be left with a crusty white solid of sodium chloride. Solubility, or this ability to dissolve in water, is a physical property. It's a physical change. The structure of the molecule does not change. And again, we'll kind of talk about solubility a lot more toward the end of the year. But right now, I should understand that it's a physical change or a physical property, because I can reverse it and get the original substance back with just another physical change. All I have to do is evaporate the water. Boom, I got the solid sodium chloride back. I can test magnetism. All I got to do is run a magnet across my sample. It's either magnetic or it's not. And I'm not changing the structure of the particles. So this physical property would be something I can observe in the lab, and it's kind of related to the idea of a physical change. A physical change would be one that occurs without changing the structure of the particle. So again, like I could mix food coloring in water, and the color of the water might seem to change, but really it's just a mixture. The H2O molecules are still H2O. They're just mixed with some other compound that's making it colored. Here's another good way of looking at it. When I picture a physical change or a physical property, think about like this idea of a phase change. So here's my beaker of water. And these little water molecules are H2O. So let's draw the big oxygen and the little hydrogen. They kind of look like upside down Mickey Mouse heads. We'll be drawing lots and lots of water molecules this year. Well, let's see if we can squeeze one more in there. There's little water molecules. Okay, so now let's say I have a phase change. Let's say I want to evaporate the water. I want to go H2O in the liquid phase and change it to H2O in the gas phase. Notice, if I write it like an equation, the H2O molecule did not change in any way. That's a physical change. It's the exact same structure. Here's the only difference. In the liquid phase, those particles are still kind of close to each other. They're flowing around, obviously. They have a little bit of energy. But if I heat these water molecules and I give them enough heat that they change phase, now I've got water in the gas phase. And we'll chuck one over here. So here's liquid. And here's kind of gas. In the gas phase, the particles have more energy, there's more space between them, they're moving around faster. That's the only difference. Maybe this guy's going over there or something like that. Instead of being in the liquid phase, where they just flow past one another, they're still kind of close to each other, moderate energy level. Now they're in the gas phase. But notice the structure of the particle is exactly the same. That's a physical change, or a physical property. Chemical properties, on the other hand, are only observed when one substance interacts with another. This will always result in some kind of a new product. There's a new product, it's got new properties, it has a different structure, like on the molecular level. It's a completely new product. Examples. The best examples I can think of are obviously like ability to burn. When something's burning, that's a chemical change or a chemical property. Let's say flammability. When something is burning, it's being transformed into a completely new substance. And again, like the chemical equations or things I will look at eventually, like if I burn wood, the original wood is a compound called cellulose. It's a compound made of carbon, hydrogen, and oxygen. When you burn that wood, you're left with just carbon. The structure is totally different. The hydrogen and oxygen are released into the air as water vapor. What you see left behind, that black soot, that's just the carbon. The chemical structure is totally different. We could make kind of a general one and just say like chemical reactivity maybe. Chemical reactivity. Will two chemicals react with one another? And if it is a chemical change, a chemical reaction, then we will form something totally new with new properties. So again, like on a particle level, here's what I kind of picture. So this here was just a physical phase change. Where the H2O was in the liquid phase, we added energy, now the H2O is in the gas phase. But the structure of the molecule is the same. Whoa. Okay, so here's what a chemical change might look like. Let's say I have that water. And I'll balance this. What if I take two H2O molecules in the liquid phase? And I add tons of energy. You can break apart that water molecule into hydrogen, which looks like this, H2, hydrogen gas, and O2, oxygen gas. So here's the chemical equation for the decomposition of water. Now that's a chemical reaction. The structure of the water molecule is totally different. It used to be two hydrogen and an oxygen bonded together. Now I've separated that into individual hydrogen molecules and oxygen molecules. in nature, they like to be paired. So 2 hydrogens bonded together, 2 oxygens bonded together. And again, eventually we'll see why. When we talk about bonding and atomic structure, there is a reason why hydrogen and oxygen like to come paired. Visually in my head, here's what this kind of looks like. Now here's 2 water molecules. That 2 out in front means 2 water molecules, which again, I'm hoping that you've done a little bit of chemistry in the past, whether you had biophys, physical science, wherever you're coming from. You might recognize some of these symbols in a chemical reaction. So the 2 out in front, this 2, means that I have 2 molecules of water. Each water molecule is 2 atoms of hydrogen bonded to 1 atom of oxygen. My hydrogens are the little dark reds, and the oxygen is the bigger atom that I'm leaving as kind of blank. These guys change. And here's what this will kind of look like. I'll have 2 molecules of H2. The hydrogens are my little red atoms. Now again, you might remember that in a chemical reaction, we can't create and destroy atoms. So originally, I did have 1, 2, 3, 4 hydrogen atoms, and I still have 4 hydrogen atoms, but they're in a totally different arrangement. I started with 2 oxygen atoms, and I still have 2 oxygen atoms. But now they're bonded together instead of being separated into 2 individual water molecules. That's a chemical change, where the structure of the original particle is totally different, and the products have new properties. Obviously, I'm starting with liquid water. That is totally different than hydrogen and oxygen in the gas phase. If you know anything about hydrogen and oxygen, individually those gases are flammable. Well, number one, water in the liquid phase is obviously not a gas, so the phase is different. And last time I checked, water was used to put out fires. So H2O water is not flammable, totally new properties. That's what I'm looking for after a chemical change.